Hi, my name is Dan Winter. I'm a psychophysiologist. I work in biofeedback and have discovered some very interesting things about the electrical nature of emotion. And in the process of doing that, we've been doing frequency signatures or harmonics of the heart at the moments when people feel bliss and joy and compassion. And we've discovered that at moments when people have intense emotions, their heart creates frequency pictures which are a powerful indicator that they're doing something electrical inside their body when they have emotions. And recently, with my friend Will here, we've been having these conversations about this Technocalypse television documentary that's kind of sweeping Europe. And we're a little troubled about a certain part of that. It has to do with the way in which they seem to be urging you to consider using little microchips and other ways to include machinery as part of biology. And they're kind of saying, well, there's nothing sacred about the shape of the body and the electricity of the heart, and machines can be doing this better. And so then we're actually stuck in the middle of something of a quandary, because my work on emotion has suggested to me that we could actually answer a profound question about what is the purpose of DNA in an entirely new way, which gives us a completely different view of what we should be doing with the relationship of technology to biological substances. So our little fun answer to this question of what is the purpose of DNA is very brief. It's called Bliss and the Magnetic X. And that's really the subject of our little story today. And it has to do with this idea that we believe we've discovered some secrets, some visions to exactly how human passionate, bliss-related emotion actually gets into the genetic material. And therefore, emotion's ability to program and shape, and we're going to talk about braid the DNA, has everything to do with the genetic material having been in this profound shape which nature put it in. And if we go messing in there with this genetic engineering and all these chips in your cells, we stand to actually affect dramatically whether or not emotion can continue to program DNA. So in order to tell you this story, I'm going to show you some pictures of what we're calling the Magnetic X generation. And it's kind of play on words from this old story of there's this, we had this post-World War II generation, the baby boom, and then there was the X generation. And the notion here is that if you feel enough bliss, it has an effect on your DNA, and we'll see that's been measured. So your DNA becomes a magnetic X. It's kind of a fun notion. So here are the pictures. First we look at this idea that, in fact, the X chromosome, which sort of determines what it is that makes woman versus man, actually has a magnetic field around it. This field is based on the geometry of the microtubules at the moment of cell meiosis or mitosis, cell division. And so you see that really this division of the DNA, the cell division moment of this living cell, is dependent on whether the X chromosome is literally, in a sense, magnetic. So the timing of cell replication, which when it's orderly it's not cancer, and when it's disorderly it is cancer, is dependent upon a magnetic field to align the microtubules and the DNA in this lovely ritual dance. So if the magnetic field's messed up, obviously the timing of cell division is going to be messed up. So we need to understand, where does the magnetic field around DNA come from? This is a picture from the early, and you can even zoom in right here. This is the early X-ray photographs of DNA when they first tried to model genetic material as having a double helix. The Watson and Crick moment was when they were able to interpret this magnetic X. They made an X-ray photograph. They said, oh, the only way you could cast an X-ray shadow of the DNA protein was to account for that, it had to be a double helix. So DNA as a double helix was first discovered specifically because, literally, the X-ray shadow of DNA was an X. It's a magnetic X. And we're going to see that has meaning in terms of what's squirting out of the places where the DNA crosses itself. Crosses itself, sort of makes a blessing. Well, the cross on the cross turns out to be the mechanism of braiding, which we'll see in a minute may in fact be emotion-induced. So what we're getting to here is there might be a reason not to mess with the spacing between the codons of your DNA. And while all these biologists who are hacking up your DNA in this genetic engineering call it junk DNA, they're affecting the spacing, which affects whether this X cross in your DNA works to make a good harmonic squirt gun, a harmonic cascade, a way of laddering the frequencies. So let's look at some more of the pictures. The idea is that in the genetic material you have a nest of magnetic fields where each of the magnetic fields is like a donut inside a donut. And when the donuts or field effects nest properly in the DNA, then they make this X, which we'll see can actually project harmonics out through the throat of the X. And this becomes a way later we can talk about how DNA gets a field effect that goes faster than light. But let's just take another little simple picture here of how the braiding works. This is like how you make a ponytail in your DNA. So the point is, what the scientists who have been talking about your DNA may have been forgetting here is the difference between the short wave, which is this helix, versus this wave on the wave, of the wave, on the wave. So you get this braiding going on, where you're going down the throat, where when finally you see this actual X in your DNA, what's actually happened is there's been a braid on the braid of the braid of the braid. And you have this very long wave now superposed in your DNA. Let's tell that story for a second, and we're going to cut to a little movie here. In order to understand our movie, we need to understand what it feels like to look down DNA as a slinky from the top. And this is the picture from New Scientist magazine, where it shows that the way genetic material looks like from the top is a 10-sided figure. Notice it looks like you have a little kind of a black hole, or a linear accelerator, or maybe a squirt gun down the center. So now we can play our little movie. Here's another view of the top down, looking into that ratcheted dodecahedron. And as that dodecahedron ratchets down, we see that the double helix in your genetic material is a wavelength here, which is, this wavelength here is in the ultraviolet spectra, okay? So it's literally a high quality ultraviolet or blue light. Later we're going to call it blue fire. But you see that we've drawn in the double helix here as a blue and purple helix, okay? And so that helix is a short wave in your DNA. But what the genetic engineers may have forgotten is they're all excited that they now understand the letters, but they don't understand how the words and the syntax requires a phrase within a sentence, within a paragraph, within a book. And it's that context richness or context embedding which is the braid on your DNA. And you see how this is a braid of the short wave on the long wave? So the information that's in your DNA actually has these waves here, which are very long waves, which is a wave on a wave on a wave on a wave waving. That's called super looping. And that's actually a picture of how harmonics nest in, say, things like your heart, where, for example, in your heartbeat, you have your heart beat as a wave, and then you have your heart rate as a wave, and then you have your breath as a longer wave yet. So you have a wave on a wave waving. And that's the process of embedding, and the embedding or nesting of how short waves can nest inside of long waves, where the interference between them is all constructive, is based on something called perfect nesting or perfect branching, which turns out to be exactly in Mother Nature what she calls phyllotaxis. And that's how leaves branch in these trees around us. In the lovely trees, the way the branch happens is that this branch, with relationship to this branch, chooses the place to unfurl so that the geometry of the leaf structure actually solves the problem of perfect sharing. So you got this one leaf that says, oh, I need to share the light so that there's maximum exposure, minimum superposition. And what Mother Nature discovered is in order to do this, the way the leaves branch is they do a 1, 2, 3, 4, I'm sorry, 1, 2, 3, 5, 8, 13. Okay? It's called the Fibonacci progression. And that progression is such that if you take any two numbers in the sequence and add them, you get the next one. 1, 2, 3, 5, 8, 13, etc. The point is that that Fibonacci progression, which is perfect branching, perfect nesting, actually leads to the ratio of the golden mean, which is called phi. Often it's symbolized by the Greek letter phi, which is a circle with a vertical line through it. And phi, the golden mean ratio, is the solution to perfect nesting or perfect branching. And we're going to see later that that harmonic ratio actually shows up in the heartbeat as the space between harmonics in the chord, the music of the heart, deciding what chord to play. And when the space between harmonics is a multiple of phi, the golden ratio, it appears people are generally having an emotion that's heart-centered or open or blissful. And so Mother Nature is solving the problem of perfect sharing by solving the problem of perfect branching, which turns out to be the solution to the problem of perfect nesting, which is the solution to perfect compression. So all of these things are related to the golden ratio or the golden mean or the sacred cut. You know, the sarcophagus in the Great Pyramid has that shape, that square, and you have that shape in the Parthenon in Athens, Greece. Okay, so sacred structures use this shape to embed magnetism. Well, it turns out that genetic material is all about that shape, and we'll see some pictures in a minute. So let's go back here now to the magnetic X, and we'll look for that ratio in DNA. So now here we have some pictures of the genetic material. And again, this is the top-down view of the DNA right here. And you can even zoom in on a bit. But it turns out that if you map the way the DNA helix is ratcheted, the golden ratio is the distance between the rungs of the ladder right there, okay? And the golden ratio squared, that's called the vertical increment of turn. The golden ratio, or phi squared right there, is the horizontal increment of turn. And then the radius of the turn, which is this distance from here to here, in angular measure, is golden mean cubed. So length, area, and volume, golden mean squared, and golden mean cubed, are preserved in a ratchet. It's a simple way of saying that no matter how you cook it, genetic material uses this ratio. In fact, if you look at the center rung, or one step on the ladder of DNA, it's one codon rung of the ladder. The geometry of that rung is often modeled as a golden ratio pentagram, stars within stars, where all the ratios are golden mean, and the center bond in the DNA down the zipper is actually, it's called a nonlinear hydrogen bond. It's often been thought of as being responsible for aging. The stability of that bond at the zipper down the Slinky is also a golden mean rectangle. And we can see that here where the actual models of how the DNA rung works. You have a pentagonal bond next to a hexagonal bond. And that 5-6 relationship right there, here shown in the guanine cytosine relationship and also in the adenine thymine relationship. These are just how the ladder or the Slinky of DNA is braided. And that brings us to the little picture of the Slinky. Let's look at the Slinky here for a second. See, what happens because your DNA looks like a Slinky is the fact that there's a mechanical way to couple a short wave to a long wave. For example, quartz is a Slinky, the SiO2, the silicon dioxide helix of the long Z-axis optically of quartz, is also a Slinky like DNA. Now, the reason Mother Nature uses Slinkies in order to teach us about how to connect long waves and short waves is very easy to understand. What happens in a Slinky is, here is my hand changing the length of this Slinky like this. Okay, that's a long wave. Okay, But as I do it, notice that the sides of the Slinky get skinnier. So I have the sides of the Slinky getting skinnier like this. See how that pulls in and gets skinnier? While the length of the Slinky is a long wave, the width of the Slinky is a short wave. And yet these two motions are connected. Long wave, sound, or stricture it's called in piezoelectricity, and short wave, or voltage. So here you have a sound wave, a long wave, connected mechanically because of the Slinky to a short wave, a voltage. And that's one of the ways in which Mother Nature uses the Slinky shape of DNA to connect long waves to short waves. Well, the fun part of our Magnetic X story is that in genetic material, what happens is the DNA is mechanically connected to the sound waves of the heart. So earlier, when we measured the harmonics of the heart, let's look at how the harmonics or the frequencies of the heartbeat actually affect this what's called context richness in DNA. In order to tell that story, I need to tell you about a book I read a while ago. The book is called Grammatical Man, Information, Entropy, Language, and Life by Jeremy Campbell. And he is discussing this problem of how genetic material got to be what he called high signal-to-noise ratio, which essentially means that, well, here's the DNA, and it's like millions of times a day taking the RNA, mating it to a DNA codon, and saying, oh, we've replicated, it's like a transistor made an accurate switching. The thing is, the DNA makes this switching operation, this mating of pairs, like sticking two pieces of puzzle together, millions of times a day. And it does it with such incredibly incredible accuracy, it's called high signal-to-noise ratio. Well, in this book by Jeremy Campbell, Grammatical Man, he tries to scratch his head and say, golly, how did the genetic material get to be so able to make millions of these information transactions and make so few mistakes? And after lots of fun in the book, he finally decides it's a language problem. It's exactly like if you had a book, and the book was made of letters. And so the letters are like ABC and all these words, and then you had a word within a paragraph, then a paragraph within a chapter, then a chapter in a book. Now supposing little Johnny got the book out one day and used his pencil and scribbled out a couple letters, and there were a couple letters missing in the book. Well, the fact is, if you were sitting there reading the book, you would have so much information about the context that, in fact, you'd be able to replace the missing letters. This is called what he called context dependency or context richness in genetic material. Well, his answer to the question of how genetic material got to be so accurate in making these information transactions was that because there is so much context richness, so much like, well, here's the example he gave. He said, if you were a computer programmer and you were trying to debug DNA, but it was exactly like debugging a program written, let's say it was written in a high-level computer language like C++. Now, in a high-level computer language, you take one instruction and you effectively have grabbed a hold of a block of machine code operations that's huge. It's like a whole nest of operations. So, in fact, if you wanted to debug some fancy program that was making pretty pictures on your screen, and somebody showed you the machine code, this little hexadecimal location that said add to and multiply over here, you'd be like in a swamp of soup that would like mess you up forever if you tried to debug the software using the machine code. So what you have to do to debug a program is look at the context or long chunks or blocks of code. And these long chunks or blocks of code is what we call a high-level programming language, which is basically like C++ or DBase. Well, the thing is, now we've got these genetic engineers today, and they just got so excited, and we congratulate them. It's very useful. But what they figured out is the letters in the code. They don't have a clue what the words mean yet, And they don't even know that such a thing as a paragraph existed. And if somebody told them there's such a thing as a chapter, the only way we discover that level of meaning in the genetic material is this thing called context richness. Now, context richness is the same thing, you see, as this embedding or nesting we just saw the animation about. So when you saw that short wave, which is an ultraviolet wave, which is the helix of DNA, that is in fact what your genetic engineer now thinks he understands. He thinks he understands how one code sits next to the other in this simple Slinky, which is useful, but it's only the very beginning. Because in fact, what happens is that now you take this sequence of a certain series of codons in this little Slinky, and you take this and you braid it into an envelope where the wave fits in this lovely little envelope. And you have an envelope on an envelope on an envelope. It's like saying, oh, the answer lies folded in an envelope. But that's easy to understand, because if you took thread and then you kind of braided it, you might have string. And then if you braided that string, you'd have a rope. And then if you braided that rope, you'd have a very fat rope. Now, if you were done, you'd have a wave the length of that very fat rope, which is a very long wave, which contains the wave of the string and the wave of the thread. But yet, if you were debugging where that rope is going, you couldn't get a clue about the meaning of the long wave by looking at just the letters, the short wave, the thread. The point is that the way Mother Nature decodes DNA is, here you have this sequence. It's like genetic material is lumped into these groups for a very important reason. It has to do with, like, the way you decode DNA is because after it's braided into the rope, the actual waves that are tucked inside do not get mechanical access to the RNA. So mechanically what's happening is the DNA, the deoxyribonucleic acid, is able to share its templates, its codons, its cookie cutters, so the half helix can say, okay, waltz in here, RNA, and mate to see if these two things fit together. That can't even begin to happen unless mechanically the DNA has access to the RNA. So from a mechanical point of view, if you're some of the DNA and you're tucked inside the thick, fat rope, you don't have access to the RNA. So guess what's happening? That particular section of code does not get read. And so, in fact, whatever mechanically does this long wave braiding in your DNA is what's called switching the active sites. The programmer. So in fact, what the genetic material has a way of deciding what groups of codes do in fact replicate. Now this has been a mystery to genetic engineers for a long time, that even in fact, say in the cases of AIDS, where you have this virus and it's there in your cell, but it appears to be dormant. And then suddenly, if you get a cold or you get depressed, and in fact, if you get depressed, you're more likely to get a cold, and then suddenly your immune system is weakened, and then this virus switches on. So what they didn't understand is, mechanically, what is the way in which a group of code is switched on? It's just like you're waltzing up this little ladder of your DNA, and because of the braid, the DNA knows read 2, skip 4, read 6, skip 4, read 2, skip 6. Now, the way that's done is the braiding. But if you're this simple mechanical engineer that has made simply a map of which codon is next to each other, knows the letters, but doesn't know the words or the paragraphs, or the context, or the syntax, then you're in big trouble, because in fact, you don't know how certain sequences of the codes are in fact deciding to replicate. Now, the really fun part of this little story that I'd like to get to, I call it the storal to the mori, which is a funny way of saying the moral to the story, is that it might just be that your emotion, this mechanical sound wave, this long wave that comes from your EKG, is in fact the way in which your DNA gets braided. See, we already know that genetic material has to have a way of making groups switched on and off. And we suspect that's what's called stoichiochemic or stoichiochemical or structure related or simply shape related. So we're not going to get to the clue of which groups of codes in DNA get switched on and off by simply looking at which little codons are in a row. We're going to have to look at the long wave structure. The long wave structure, as we just saw from the braiding animation, is in fact an image of how sound waves, or very long, it's called phonon, which is just a name for sound in a liquid. So you have these sound waves or phonon waves, in fact, mechanically braiding your DNA.